Thank you, Kartik. I want to thank Joachim and the organizers for the invitation. This is my first time to Vienna, and I've really enjoyed it. I've also this has been a conference where I feel like my mathematical horizons are broadening, so I've really appreciated it. So thank you very much. Okay, so I want to tell you about some recent work of mine that's joint with two co-authors, Jingwei, Xiao, and Zhang. We're interested in, well, the central values for, I guess I'll say, standard L functions for for cuspidal representations on GL2N. So in particular, we're only going to be seeing symplectic, things of symplectic type today. So I want to start off with just some notation. They'll come over here. So just to begin with some motivation, I'll just fix number field K, or sorry, number field F. And there will be some extensions of F that show up, so I'll try to stick with the subscript for the Adels. GB connected reductive group. For F, and we'll be interested in periods of automorphic forms on G with respect to certain subgroups. And so just let H denote a reductive subgroup. And let pi be some irreducible cuspidal automorphic representation of G. Okay, and so what we're interested in is the period integrals. What are my notation? So we're interested in is if I take a vector phi inside of my representation pi, then we're studying. There's lots of different things that could be meant by a period integral, but I'll just stick with the, for the most part, for this standard notion, where I pull back to the subgroup, and then I integrate over quotient. Maybe I have to mod out by some part of the center, but it doesn't really matter for this talk. So this is the period integral, and we'll say that so we'll say that pi is H distinguished if I can find some vector phi here, so that this just is not very weak, not zero for some phi. And so in general, we're interested in understanding what the spectrum, what possible representations pi supports some period, and so we would like to classify these. And hopefully, as we've seen several times already this week, we can interpret this in terms of some L functions. So the motivating example to try and understand this is some old results of Friedberg and Jacquet. Who considered the case, I guess this was in like the mid-90s, they considered the case of just a maximal Levy subgroup inside of GLN, but I'll just specialize to GL2N. I'll take H, the so-called linear period. And they were able to prove what is in some sense like the best case scenario kind of result for what we'd like to see. What did they prove? That so pi is H distinguished write that out, GLN cross GLN distinguished, if and only if the following two things hold. One, pi is symplectic, of symplectic type, which has shown up many times already, and just to recall, means that be functorially lifted from some odd orthogonal group, and that can be encoded by saying that your square L function has a pole at s equals 1. And a second condition, which is more subtle, that the central L value of pi is non-zero. So this is what they were able to prove. And in fact, you can do better in this case. You can get an explicit relationship. So in fact, there exists a vector inside your representation. So this will be, say, some pure tensor, such that this period integral actually has an explicit relationship with these L values. Namely, you get the central L value times the residue. I guess there's maybe a small fudge factor that I'm ignoring. Residue of this exterior square. And then you have some contribution of all the local factors. So these some local functionals, I'll just call alpha v of PV, where these are all some sort of local period. This is this is the kind of formula that, for example, we saw in Bin-Young's talk a couple days ago, where we have some global period is equal to a product of local two periods, and the L value that we're interested in shows up as the constant proportionality. And so this is kind of the motivating example for a lot of things that go on in the study of period integrals in the so-called relative Langlands program. But I'm particularly interested in trying to understand this case, or rather a unitary variant of this. So I want to study unitary variants of this. And so what do I mean by that? I mean the following. So this could mean a lot of things, but we'll just start off with, so let's fix E over F some quadratic extension. And I'll take V to be some 2n dimensional Hermitian E over F Hermitian vector space. So with this, I can choose my G to be unitary group. So it's 2n. And for H, I'll do a few more examples later, but what we would like is that we could find a decomposition, say W, direct some perpendicular part where the Hermitians, these are both non-degenerate summands, and so, and we'll assume that the dimensions are equal. And so then given such a decomposition, we get the subgroup UW perp as a subgroup. And so this is what I mean by studying a unitary variant of this. So the so-called unitary Friedberg-Jacquet periods. And so there's a couple reasons why you might be interested in doing this. Why I care? Well, so there's a couple of things I want to say. I mean, first is that when you're in the unitary case, we can now be interested in the associated Shimura varieties. So this gives class or cycles. I take the Shimura variety for this product of small unitary groups, and that I can obtain, I can do that inside the Shimura variety for the larger group. And there's a lot of flexibility here, where, for example, if you're interested in sort of cohomological questions, you can sort of vary the data here so that you get things in middle degree or in other degrees if you're interested. And there's also cases where, if you assume for, I guess here I'm assuming like E is CM or something like this. So that's more varieties, but in general, there's no constraint. But one thing that's of particular interest that I won't say much about is that we can obtain cycles in middle arithmetic degree. So we can spread these out over some integral structure, and then we can try to understand intersection pairings appropriately, and maybe study these for higher rank generalizations of Gross-Zagier. So that's one source of motivations. But another is just that it tends to be that this seems very closely tied to the L values that show up in this theorem of Friedberg and Jacquet. The second is just I've started. So let's assume that pi on GL2N AF has an H period, so I'll GL n squared period. Then we know that it has to be symplectic, so in particular it's self-dual, isomorphic to its controgradient. And so I've just picked some arbitrary quadratic extension. So for any E over F quadratic, I can consider the corresponding base change to the quadratic extension, just cyclic base change. And now I have an automorphic representation on GL2N over this field extension. And so I'll assume, let's assume for simplicity, that this bigger representation on the bigger group is cuspidal. Call this guy pi. Well, okay, so since pi itself was self-dual, so this will imply that pi, the capital pi, is also self-dual. That's easy. But moreover, it's arising as a base change from GL2N over the ground field, and so it's also, just by the theory of base change, it'll also be, I'll say sigma, a Galois invariant, where sigma is the generator of the Galois group of E over F. And so if we put these things together, okay, this is not that hard. I'm sigma. I'll put this one on this side. I'm also a conjugate self-dual. And so by the theory of, I guess this comes from Mach, that when I have a cuspidal automorphic representation on this linear group over the quadratic extension, this means it has to have arisen as a stable base change for some cuspidal automorphic representation where pi g is a cuspidal representation on some unitary group, so one of these U2Ns. Okay, and so if I just start with something that has one of these periods and I consider the base change, I automatically descend down to some unitary group. And so it's natural to ask if this thing downstairs has a period that looks like this, and if we can somehow relate these period values to the L function. Yeah. Maybe with some of the strong assumptions I'm going to impose, that's true, but in general. So in particular, I'm going to slip. What I want to say. So I want to see a picture. Let me just maybe put a little diagram to keep track of. G will denote my unitary group, which I'll just allow to kind of be variable at the moment. And so this will be base change. Later on, there might be a couple different base change maps, so I just want to fix some notation. And I'm going to adopt the notation that G sub 0 is the linear group over F. And so we're in a situation where I have some cuspidal symplectic guy on this linear group here, and I have some cusp form on this unitary group, and the relationship is that their base changes agreed. That's the sort of context for the conjecture I'm about to state. Do I want to say anything else? So let me go ahead and state the conjecture. So we state this this is a special case of a more general conjecture that I'll say a little bit about in a minute. But I think in this case, this conjecture probably goes back, I think Jacques probably knew about this a long time ago. There's certainly a few like low rank works that are related to this. And we did, I mean, so there's several, I'll make a comment about other works in a minute. Okay, so let's be in this context. So I'll assume that pi naught is cuspidal on G0 AF of symplectic type. And I'll assume that its base change to E is cuspidal. Preferably, we would like some formula as when we get in Friedberg-Jacques, but we're going to state a qualitative conjecture. Then the following are equivalent. So I need not just the central L value, but I want the central L value of the base change. Is non-vanishing. The second is that there exists a unitary group U B, which is a rank 2n, and a cusp form Ig as above, base change Ig with, I'll say it this way, with pi G H distinguished. So for in particular, what I mean here is I have this Hermitian vector space, which for which there exists a decomposition as before, and that gives me my subgroup U. That's part of the statement. Are there any questions with that? Okay, so let me just say a few things. So versions of this conjecture, I think, appeared with talks of the other two authors pre-COVID. And so there's a couple of works that had appeared in the meantime studying aspects of this conjecture. And so, in particular, much stronger, okay, I'll say much stronger than what I'm about to say. So results in the direction of the form. Always get this wrong, and I forgot to write it down. It's WeTech is in the room. L value implies period was what you guys proved. Is that correct? Which direction did you prove? I always get this wrong. One of the directions is, yeah, okay. It's in the paper, but like when I'm on the stage, I cannot remember. So so results of the form that the period non-vanishing. So this is a statement that a particular period is non-zero. Implies that an L value is non-zero. Are known. So there's two pieces of work in this direction. So as I alluded to, a paper of WeTech and a student, Rio Chen, consider this by data correspondence techniques. And prior to that, work of Aaron Pollack, Mikhail Zaidor, and Wan. I guess I swapped that, sorry. Prove this the same direction using residues of Eisenstein series. And so there's been a lot of work in this case. And so what let me go ahead and state our theorem. Okay, so the conjecture is true, but we're going to make a lot of assumptions. So under certain local assumptions on the representation pi naught, and also on the field extension E over F. So this is one of these things where the point was to, as I'll get to in a few minutes, introduce a comparison of relative trace formulas to try and establish this in general. And we're able to get a lot of the sort of local results that one needs, but just not enough. And so what these local conditions are just what we need to establish a simple trace formula. So the kinds of things that I mean, they're actually reasonably strong. E.g., like E over F is everywhere unramified. And maybe a few small primes split. Some conditions like this need to be imposed, and pi naught also needs to be supercuspidal at two places. And unramified at non-split finite places. I'll say inert places. Okay, I'm not going to get into the weeds of the simple trace formula, but just to sort of give you a sense of the result is, the point of this theorem is really that the method is to introduce the method, namely this comparison of trace formulas that I'm going to discuss in a bit, and also to, like, the main hard work that goes into this is establishing the various fundamental lemmas that are necessary. And in particular, we have to deal with some new phenomena that I'll try to get to towards the end of the talk. Okay, yeah, so there is an additional Archimedean condition. So obviously, it's fine if the Archimedean place splits, but if the Archimedean place is non-split, so you see over R, we need that pi naught, the base change, is in the descends to the compact unitary group. So we're able to do compact at infinity, but the sort of, we need to do some more work to drop that. But for example, we could put, like, trivial infinitesimal character is okay. Okay, so I want to try and spend a few minutes talking about, we actually are interested in a much more general setup than just this. And in particular, I'd like to state another theorem that's like a variant of what this picture is. But I just want to make one remark. So in this world, there's these sorts of qualitative types of statements where you have a non-vanishing of an L value if and only if a period integral. And this is a sort of result of GGP type. And you might also be interested in a quantitative statement where you explicitly relate the values. And so in this context, we expect formula where, so I'll take my period integral over my phi, exists phi in my pi g, where if I take the period over my product of unitary groups, I need to take its exterior, or its absolute value squared, but then up to some constants that I'm not going to specify. This is given by the central value times some local factors. Beta v. Okay, so we expect a formula like this. And the problem, and I want to say this in a very narrow range. So there's a lot of things, we don't expect this to hold, for example, for all cuspidal automorphic representations on the unitary group. Only for the ones that maybe, as the conjecture is stated, might you get this. In general, we have lots of interesting phenomena where these local factors don't behave as they do in the context of GGP. But at least in this case, we do expect this. And I sort of realized after we already posted the papers where we prove this, that when E over F is Cm, and pi g is, we can actually prove this, just like our results allow us to prove this and prove this certain g. And so there is something like this, but a lot of interesting things come up that I'd like to indicate later in the talk, so that it's just not going to be as simple as this in general. Okay. Okay. So do the thing. So I want to make a few comments about a more general statement. So, you know, one thing that sort of motivates what I'm about to say is that we want to somehow come up with as many algebraic cycles as we can, and for that we are there's a more natural setting where instead of just considering this decomposition, we consider the following. So I have my field extension E over F, and I'll fix a second quadratic extension. And so that gives me, I guess, what we call the biquadratic setup. So there will be some third field, this. And we have, so given our permission space, V will let this field F prime act. Given action of F prime, F prime will act unitarily on V. And so that gives me the structure. So I have some n-dimensional Hermitian. So this is n-dimensional E prime over F prime Hermitian vector space. And so I realize V as a restriction of scalars from F prime down to F. This. And so in particular, we can take the unitary group for W and do the restriction for scalars. And that can be my subgroup F, G as before. And really, more generally, we would start with this biquadratic setup, and instead of taking just a Hermitian space, we would consider a more general central simple algebra with an involution of the second kind. So that gives us inner forms of these unitary groups. And so there's a even more general picture than this. But I want to just isolate two examples. So if F prime here, so I've just fixed this field extension throughout, but I can allow F prime to be a sort of split extension. Then this actually just recovers the example over there. Then H is UW. There's some, this corresponds to a decomposition as before. I guess my notation is bad now. Maybe I'll call this V prime. And this is the decomposition that we saw before. So that sees how the prior example fits. The other natural thing to do would be to just allow the two extensions to be the same. But then this restriction becomes, this extension becomes split. And so it turns out that what that means is that this unitary group here is just a linear group. Where X here is some isotropic subspace. So I have some polarization, for some polarization here. Okay, so this is another way that I could have generalized the notion of the period that Friedberg and Jacquet considered. And these just arise as special examples of this more general setting. But the reason I want to mention this is that is two reasons. That this more general picture actually is of interest to the applications to Shimura varieties, but we also were able to prove a theorem in this case. And one of the things I want to highlight is by studying these two examples, we kind of see some interesting phenomena that is necessarily embedded in this more general conjecture. Let me go ahead and say what the theorem is. All right, yes? I'm sorry, that's hard to read. there exists some n-dimensional vector space E prime over F prime Hermitian vector space. The action of this field, or this a unitary action, I'm just embedding an involution inside this unitary group, but I'm interpreting it as an action of the quadratic extension. And so the point is there's some n-dimensional Hermitian space over the larger field associated to this extension, and I can take the unitary group for that. And then if I restrict scalars down to E over F, that gives me my subgroup. Sorry. Let's state the more general conjecture. Yes, okay. So, sorry, let me state the conjecture first. It's just the point I want to make is that we get this situation where there's these three quadratic extensions showing up, and in general, all of them play a role. So the conjecture is that, let's assume pi naught is as before, meaning as stated in that conjecture there, then the following are equivalent. So now I'm in this situation. I have in general two quadratic italics F algebras, and I have these three fields, and so the L function now splits. There's now no longer just a simple statement of this form, but the conjecture is that you can either consider this L value, central L value, but where I'm taking the cyclic base change to this middle extension, why not? Or do the same extension. But first, pi naught has to become twist. You have to twist by the quadratic character for E over F. Theta E over F is the quadratic character. Associated to the extension. So this is the L value that we can say in this case, and the alternative is the generalization of that. So there exists a V with a structure of as before, namely there's some an n-dimensional E prime over F prime Hermitian space V prime, and we'll set V to be the restriction of scalars down and IG hospital on which is distinguished and the same thing as before. The base change of pi g agrees with not the base change that shows up in this theorem, but the original base change that we saw in the previous. You really have, there's the F prime shows up in defining H. There's the F prime prime here, and you have E built into the group. So this is the conjecture in general. And in particular, you have this strange ambiguity where it's not one L value. These are genuinely different L functions, and it's not, as we'll see, it's not like a weakness of the, it's an if and only if, but it really, you see in some interesting way this sort of, these two L values showing up, which in some senses should be related to, in general, something more complicated than this kind of a formula is happening. Okay, so the theorem. So if I come back to this case here, we've already seen what it's maybe a bit of an exercise, but this conjecture reduces to that one in this split case. In this case, these two the L values become, right, so these are all base change L functions to some cyclic extension, so it's just a product of twists of the standard L function. And so in this case, what happens is you either get the standard L function squared or standard L function twisted by this quadratic character. Right. These are the two L functions that show up in this conjecture when we're looking at this Ziegel levy. And so that's the theorem. The conjecture holds for f prime equal to E, so this case here, for under the same local restrictions as in the previous theorem. Okay, so I have, so namely either, so in this case there's no base change, e.g., so the result is just either L of 1/2 of pi is non-zero or the quadratic twist. Whereas in the previous conjecture, it was the product of them. That's the base change. So there's something different that happens in this case where the two L values split apart. And I'm going to say, hopefully see something in the trace formulas that indicate such a thing, such a behavior. Okay, so the plan of attack for these sorts of results is a comparison of trace formulas. And so on the so I'm going to have two trace formulas, one on the unitary group side and one on the linear side that's encoding the L function, and then we'll try to compare them. So on the unitary side, this is just the classical Jacques style relative trace formula for these periods. So I get some distribution that I'll say I'll just fix for simplicity this notation where H could be either of our cases or the levy. So the relative trace formula is just the integral against this period for the automorphic kernel. So I'll write this out because it hasn't appeared in this this conference yet. Okay, so it's the very just the classical Jacques style relative trace formula, and I'm going to impose some conditions satisfying some local conditions. That is really where the local conditions in the theorem are coming from, so that this actually is convergent, and we have the following kinds of expansions. So I'll be very coarse here. The point is you have some expansion over distinguished representations, pi g, and something which encodes this period integral, f of phi is in some basis. So this is the spectral side, and on the geometric side, let me keep these up for the remainder. It's just a sum over these double cosets, some unfolding. There's some factor here, and and the so-called relative orbital integral. And so the interesting trace formula is what happens on the linear side. So let me go ahead and say that. Describe that quickly. On the linear side, we're going to use so what we use is the linear period that showed up in in Friedberg and Jacquet's work, but we're also going to use something due to Bump and Friedberg. So we're going to use so-called Bump-Friedberg integral. What that means is I'll take some Cuss form in my representation on, so this is on GL2n, and I'll take a Schwartz function on vector space. And so what is the Bump-Friedberg integral? So it's going to be dependent on these data. It'll also have a complex variable. We'll just start with that. So it's the integral over GLN cross GLN. So I'll write this as phi h of 1, h2, and then there's some h1, h2 inverse, and then there's some absolute value of the determinant. And then you have an Eisenstein series, so that's the connection to Eisenstein series in the talk, where I take superscripts here, subscripts. I take the second variable. How did I normalize this? It doesn't matter. Yeah, H2. So it's an Eisenstein series on 1 factors of the GLN, built from this theta, and there's this phi pH. So here, this Eisenstein series is the usual mirabolic Eisenstein series. That's just a mirabolic Eisenstein series that you can build from the Schwartz function. And what Bump and Friedberg prove is that this actually gives you a very nice integral representation associated to the linear period that we saw before. So what we'll get is precisely s of 1/2 of this central L value times s plus 1 of the exterior square times a product of local guys. This is Bump-Friedberg from 1990. And in fact, we're actually going to need a little bit more. We're going to want to insert 2 quadratic characters because we have this arithmetic information from these 2 extensions, and we're going to want to maybe insert eta 1 of h1. And you can also insert a character into the Eisenstein series. Character of AH here. So there's some slight extension where you put quadratic characters in, and that's what we're going to need to get all the base change-off functions. Okay, but now we're able to write down what the RTF is. So some quadratic characters, eta 1, eta 2. So I'll take f prime on GL2 and AF, and phi as before. And so this is just built out of, so I have GLN squared cross GLN squared. I'm going to do f prime. So I have one copy. So it's strange. There's 4 copies of GLN here. So I'm going to have some character on, let's say, eta 2 on H of 2. But then I put an Eisenstein series on. I take the second factor of the first copy of GL2 cross GL2. And then I have my 1 H 1 2. So there's some complex parameter here. And the goal is that, so the point is that there is some expansion not symplectic, and some geometric expansion prime, where there's these relative orbital integrals, eta 1, eta 2, prime, d prime of S. And so the point is that this distribution here is provable to, this is not 0 at S equals 0 if and only if the claims in the theorem holds. So the appropriate L value is not 0. So in the last 6 minutes, let me just say what actually happens. So what the point of the strategy is that we want to compare the geometric sides geometric sides. So what I mean is that there exists a natural map. It's very easy from the unitary, these sets of double cosets occurring on this side. Call this guy chi, to the sets of cosets on the linear side. And what one would like to do is to, with respect to this, establish a matching, by which I mean, so some function on the unitary side matches with some pair on the linear side, so that the orbital integrals of f at gamma on the unitary side is equal up to some transfer factor, which is just a sign in this case, to these these more complicated things evaluated at 0. So that's the kind of thing that one would want, just term by term. I don't know if this is clear, but these are just the terms occurring here where I've evaluated at s equals 0, and this is the goal, to find some matching of functions. And so the main problem, which has been a focus of my work over the last 4 or 5 years, is that these trace formulas here they have the same sorts of issues that arise in the Arthur trace formula. They are not stable. Some property, some notion of stabilization needs to be developed in order to understand these trace formulas better. And in the context of this picture, chi is just not injective. And what I should really say is maybe there's some notion of regular semi-simple, so that this is actually a problem. Like these is not injective. You have an issue of orbits on the unitary side, which are stably conjugate to one another, and that's being encoded by the fact that I can't actually match orbits. I can take some finite set or some sets of orbits and associate it. So this formula, as stated, just doesn't make sense. So what one does, so one needs to stabilize this RTF that occurs on the unitary side. And in the last 2 minutes, let me just say, this following statement is a theorem of mine that shows up over several papers, but so when H is UW cross UW U inverse, or U perp, there is some notion of a stable relative trace formula. There's some notion of endoscopic. There's some notion of endoscopy in this context. And so what one gets is that there's an appropriate notion of stable RTF for F, which we can compare. We can, this stable piece, we can fix this by putting S's stable, studying stable orbit and stable orbital integrals. So we can compare this object appropriately to this linear side at 0, and so this is one of our main theorems, but there are these endoscopic terms. So this looks like this. A plus B goes to N, I guess both greater than 0. There's some constant, and there's some stable RTF on smaller rank variations of the same problem. So what this is you have some endoscopic group, which is U2A cross U2B. This is an endoscopic group in the sense of Langlands and Kottwitz, and there's, in fact, a notion of an endoscopic. This is sort of couched in the language of endoscopic symmetric varieties, but in any case, there's some good notion of an endoscopic period integral, and in this case, it just happens to be just smaller rank variations of the same problem. Okay, but in any case, I wanted to say that, but under our local conditions, this term just vanishes. So all we're left with is there's some simple trace formula so we can make this comparison. We still have to do, proving this identity is 150 pages in this case, but we're able to make this work. And that's what gives us the main theorem for this case. I'm out of time, so I'll just say out loud, when I consider the other case, well, I don't want to belabor the point. This case exhibits some brand new information or behavior that doesn't occur in the Arthur trace formula. In particular, we're not able to do there's no such thing as a sort of simple trace formula reduction like this. You have some genuine new behavior, and so there's two main terms, and so we actually still have to effect an endoscopic comparison to, in this case, to obtain our main result, or stated here, and this is related to these two L values. Okay, sorry for going over.